Imagine gazing upon the moon one quiet evening, looking at the impact craters, the structures, their outlines. As you look across the surface, at the intersection between daylight and nighttime, where the moon begins to hide in a shadow, a bright light shines an eerie glow. It was a nuclear blast. In the late 1950s, this wasn't science fiction. Inside secret US Air Force rooms, real scientists calculated real trajectories. They worked out the real yields and even the brightness of a detonation on the lunar surface. It was called Project A119, and for a moment, the world came frighteningly close to turning our closest neighbor into a stage for our nuclear theater. The story begins with a beep that echoed around the world. October 4th, 1957, the Soviet Union launched Sputnik 1, the first human-made satellite. It was a metal sphere, barely the size of a beach ball, but its signal pierced American confidence. If the Soviets could loft a satellite, perhaps they could also loft a nuclear warhead across the ocean. Newspapers screamed of a missile gap. Politicians warned of failing behind in a new domain, space. In this feverish atmosphere, prestige became a weapon. Space was not only the high ground of science, it was a billboard for ideology and warfare. Whoever achieved the biggest spectacle would win the loyalty of a frightened world. And so, American strategists asked a chilling question. What if we proved our supremacy by making the moon itself glow in light? In 1958, the US Air Force quietly commissioned a study with an innocuous name, a study of lunar research flights. Inside, it held plans for a very different mission: deliver a nuclear warhead to the moon and detonate it where the flash could be seen from Earth. The objective? Primarily public relations, as well as international diplomacy. Physicist Leonard Raffel, who led the project at the Armour Research Foundation in Chicago, later admitted that the military wanted a spectacular demonstration to reassure the world of American might. A peaceful scientific side benefit, studying lunar dust and space composition, was added almost as camouflage. Among the young researchers was a graduate student, whose name you might be familiar with, Carl Sagan, tasked with calculating how dust clouds would expand after the blast. His equations would help scientists and the military determine whether the explosions would produce the desired light halo that would be visible to backyard telescopes. Initially, planners considered a hydrogen bomb, but early rockets couldn't lift such a heavy payload. Instead, they settled on a smaller W-25 warhead, roughly 1.7 kilotons, about 1/10 the size of Hiroshima. The target? The moon's terminator, the line between night and day, so the explosion would be dramatically backlit by the sun. Contrary to Hollywood instincts, a nuke would not spout a mushroom cloud on the moon. The moon, of course, has no atmosphere, so instead, the blast would erupt eerily and silently, flinging fine dust hundreds of kilometers into space. For a few fleeting minutes, sunlight would catch this expanding veil, creating a bright flash, perhaps visible to people on Earth, with binoculars and other mechanisms. A silent, ghostly beacon proclaiming, "We did this." But attempting that kind of spectacle, of course, came with a tremendous amount of risk. A launch failure could scatter radioactive debris back on Earth. Even a successful detonation threatened future science by contaminating pristine lunar soil. Inside the Air Force, enthusiasm began to cool. Unknown to most Americans, the Soviets were hatching their own plot. Their Project E4 envisioned a nuclear explosion timed with a lunar eclipse, so the observatories worldwide would watch the flash. Like the US plan, it promised global prestige, proof that Soviet rockets not only reached the moon, but carried with it the ultimate weapon. Yet Soviet engineers faced the same obstacles: technical uncertainty, political danger, and the dawning realization that the world might recoil in horror rather than any type of admiration. By early 1959, both projects were dead. The US Air Force quietly concluded that the risks by far outweighed the propaganda value. the Soviets reached their own conclusions. Instead of nuclear fireworks, both nations pivoted to a more inspiring contest: who could reach the moon, land, and return alive. The decision, of course, as we know, reshaped history. Rather than scarring the lunar surface with radioactive dust, humanity left footprints and flags. The Apollo program turned a potential act of cosmic vandalism into a triumph of exploration that we know today. Project A119 remained secret for decades, revealed only in the 1990s when researchers uncovered Carl Sagan's scholarship application mentioning radioactive contamination of the moon. Its quiet cancellation helped spur international safeguards. The Partial Test Ban Treaty of 1963, banning nuclear tests in space, and the Outer Space Treaty of '69, which to this day still forbids weapons of mass destruction on any celestial body. Today, nuclear technology is returning to the moon, but in a much nicer and new guise. NASA now plans small fission reactors to power future bases. Russia and China discuss joint nuclear power stations. The same physics, once aimed at destruction, may soon help keep astronauts alive through lunar nights. What does this strange episode teach us? That fear can drive dazzling ambition, but also reckless and terrifying imagination. That science, when entangled with politics, can either serve wonder or terror, and that restraint can be as powerful as action. The moon ban has been a mirror. In the 1950s, it nearly reflected the worst of us: our hunger for dominance, our willingness to scar the heavens for prestige. Instead, it now reflects something much better: a species capable of pulling back from the brink, choosing footprints over fallout. So the next time you look up at the night sky and see a silver glow of the lunar surface, remember that it might once have carried the dim scars of nuclear flash.